Okay, this is Proteins and Peptides Part 2C3, dealing with, we've been talking about the chemical synthesis of peptides. We looked at protecting group strategies, coupling agents. So what we're going to focus on today is something called solid-phase peptide synthesis, often abbreviated as SPPS. Okay, so before we talk about solid-phase synthesis, I first want to talk about, the peptides that we've been making, okay? And so far, the peptides we've been making are relatively small. The example we did in class, we did like a trimer, the last presentation, and a dimer. And this solution phase, so solution phase meaning the mixing things together in a solution, purifying that compound, and then taking that new compound and recoupling it to something different is actually a very long and tedious process. So solution phase synthesis is very long and tedious, and it's okay if you're doing something that's short, but if you're doing something that is actually quite long, like a 20 mer peptide or even longer, then it's actually very, very cumbersome. So for longer peptides, we use something called solid phase supported synthesis. It uses a protection activation strategy. The difference, though, is that the molecule is actually attached to the solid support. This is similar to oligonucleotide solid phase synthesis. I know we haven't even talked about that yet, but when we do talk about it, there will be similarities. So before I talk about solid phase synthesis, perhaps I'll come back to the slide. And I just want to talk to you a little bit about what it actually is. Okay, so what does solid phase actually mean? All right, so we can actually purchase these solid supports, and they look like little grains of sand. Like if you were to actually keep some in your hand, they look like pellets. But what they are is they are mainly like little glass beads, and essentially the chemistry is done on these beads. So I want you to imagine that you have a bead, okay, and it's circular, and attached to that bead, it's covered in these amines. Okay, so think of a functionalized grain of sand. All right, and you don't just have one bead, you actually have, thousands and thousands, many of them. So what you do is you put them into a little column, and then attached to this column is a frit, and then after the frit is sort of a funnel where liquid can pass through. So let's put our beads in, and every one of these little dots corresponds to one of those beads. All right. So the first thing we're going to do is we're going to start building our our peptide off of this solid phase. So this is an amine here, and you know that to make a peptide bond, you need to take a carboxylic acid. So let's take an amino acid. Let's just give it a R1 protecting group. And then attached to that amine here, we're just going to put a protecting group. Okay. Now, in order for this amine here to react with the carboxylic acid, you need a coupling agent. So what we're going to do is we're going to add a coupling agent. And let that stir, let that mix. And then what's going to happen, though, after that reaction is that you're going to have a lot of you're going to have a lot of soluble byproducts. So what you're going to do is in step 2 is you're going to now wash the beads with excess solvent, and all of the byproducts and solution will pass through. The frit is solid, and only solution passes through. So if we take a look at what this looks like, if we take a look at what this looks like after this coupling reaction, what you're going to have are these beads still stuck in here. And these beads are going to look like this. So instead of amines attached to it, you have done an amide bond coupling. So you now have amides. You have that R1 NH protecting group, right? And you're going to have this at every single place where you had an amine previously. Okay, so we're growing our amide bond off of that amine that we initially had. Okay. So in order for us to grow the peptide further, what we need to do is we need to deprotect the protecting group, and we need to convert these groups to amines so that we can couple the next amino acid. Okay, so it's relatively straightforward. You would go number 3, you'll do a deprotection. If it's bond protecting group, you'll use acid. If it's FMOC, you'll use base. And then finally, you'll wash the beads with solvent. So again, that will push all the byproducts in solution, and you'll be left with beads that now will have this protecting group removed. So here is your column, again, with your frit and then your funnel. And these beads here, what they will look like, and just to be clear, let's draw what these will look like. They will have amides, R1, NH2. Okay, so you can see here now that by removing that protecting group, you have now made new amines, and these new amines can now be subject to new coupling conditions, right? So you now take these beads and then you go back to the cycle and you repeat steps 1 to 4 to generate the desired peptide. So you'll use a different amino acid now with R2, and then you couple, wash, deprotect, wash, and you do the cycle over and over again as many times as you need to. The advantage of doing this is, as I mentioned, you don't have to do cumbersome purifications after the deprotection and the coupling step. Okay. The other thing too is you can use a lot of excess reagent and coupling agent to push the reaction, because all that eventually get washed away. So typically the yields are much higher for these types of reactions compared to solution phase synthesis. So I will just go back to the slide that I had previously. So this first peptide synthesis actually was reported and performed by Bruce Maryfield. He actually won the Nobel Prize in '84. He first reported it in 1963, in which he developed insulin on the synthesis of insulin on solid support. It's a polystyrene resin, which we'll talk about in a second. Support is functionalized for attachment. We just talked about that. We'll be looking at a variety of different modifications of this resin. And you can make 30, 40, 50 more long peptides with high efficiency. Just to give you an idea of what this looks like, is that if you have very high coupling yields, 99% per step, and if you take that and do that 30 times, your overall yield will be 75%. All right. However, if you don't have such a good yield, let's say you have 95% yield, and you do that to the power of 30, and I'll just try to grab my calculator quickly here to see if I can calculate that. To 0.95 to the power of 30, your overall yield is now only 21% yield. Okay, so if you do that 30 times, so you can see that while 95%, 99% sounds pretty good in both cases, if you do this sequentially, you get a huge drop in yield. Okay, so it's really important for solid phase synthesis that your yields are as high as possible. And this is where some of those coupling agents like PIBOP and those really, really good ones are actually really important, because the longer the peptide, the greater the yield for each step that it has to be. Okay, so once you make your peptide on solid phase, the last thing you need to do, okay, is you need to remove the peptide from the solid phase support. Okay, so number 5, remove peptide from solid phase support when finished. Okay, so we will talk about how these are actually manufactured in one of our course pack sessions. But essentially what happens is that you have these polystyrene beads here. So you can see here that we have these phenyl groups with these styryl allyl groups here. Through radical polymerization, you can form a network of carbon-carbon sp3 carbon bonds, and then you can functionalize them with like a benzyl chloride group, okay? And these benzyl chlorine groups are the functional groups that we can now serve to anchor our sort of our functional group of interest in order to start the synthesis of peptides. This is from the textbook, just showing what the beads look like under a microscope. So they just look like little pellets, little grains of sand. All right. All right. So how do we functionalize the resin? Okay. So keep in mind and remember that we're going to now draw our solid phase resin as the circle here with now chlorine attached. And what that really means is that we have a benzyl chlorine group attached. All right, so how do we functionalize the resin? All right, so here's your resin, chlorinated resin. You can purchase those. So here's your bead. So before we put amines attached to it, as I mentioned, you have all of these benzyl chlorine groups attached to it, right? And it's of course more than just 3 that I'm showing. It's a circular molecule with many groups. So one of the things that we do is we need to functionalize a resin, and the most common way, or one of the most common ways, involves using something called a rink amide resin. And what it is you have this rink amide functional group here, and this has to interact here to generate a new functionalized resin. Okay, so what does that look like? Give you a couple seconds to think about that. And I want you to think about, just classic organic SN2 chemistry. All right, so if you look on this molecule here, your nucleophile is actually the hydroxyl group. And the hydroxyl group will come and do SN2 on that benzyl chlorine group. So what you'll end up getting is a bead that will look like this. And I'll kind of keep that first styrene group attached. You have an NHF-MOC group. And then you have the rest of the molecule. So on the rest of the molecule, there are no other nucleophiles, okay? So this is done, on all the other sides as well. Okay, so this is called rink amide. It's often abbreviated as, this here abbreviation, rink amide or rink NHF-MOC. So at this stage here, before we start making and building our peptide, we need to have an amine, right? So recall back to this slide here where we had an amine, right? That was served as our initial core to synthesize the peptides. So we need to generate that amine. So you know how to remove F-MOC, right? We've talked about that in the protecting group unit. So to remove F-MOC, you use 20% piperidine right, which is this structure here. So usually it's a 20% piperidine in solvent, so that could be dichloromethane or DMF. But the point is that once you generate the structure, what you will end up getting is the same structure that I've drawn to the left, except that the F MOC group is removed, and now you have an NH2 group, which is your amine that can now react for peptide bond synthesis. Okay, so I hope you can see now that the overall synthesis, we can use this for amino acids that are natural, but we can also use unnatural ones as well. Here is the structure that I drew. This is the abbreviation. So you can see here that there's going to be a pattern now, right? So just like we did on the previous slide, we deprotect 20% piperidine. Here's your rank NH2. And then what we want to do is we want to start building on amino acids. So amino acid with, you got to add your coupling agent. And then number 2, you need to then deprotect the protecting group from the NH group, because that amino acid has to be protected. If you don't protect the NH2 group of that amino acid during coupling, then you're going to generate all these polymers. Deprotect the NH group, and then you can undergo coupling over and over again, right? So you can see 1, 2, coupling reagent, 1, 2, coupling agent. And I've color coded this so you can see that, okay, you can basically pick your flavor and whatever amino acid you want and start growing your amino acid on that peptide chain. Okay, a little closer look at some of the chemistry and chemicals involved. Here's, again, coupling amino acid. It's protected with FMOC. And often we use coupling agents like HBTU. Okay, you could use PIBOP or some of the other coupling agents, but for solid phase synthesis, this is a common one. And then you need to remove the FMOC, so 20% piperidine now generates this free amine. Okay, so you can see the pattern: amino acid, R2, FMOC. Remember, you got to add coupling agent, HBTU. And then here, you got to remove the FMOC. Okay, so you're going to use 20% piperidine in order to do that. So you repeat steps 3, 4 if you're doing even longer, 5, 6, 7 for as many times as you need to. So at the end of the day, you're going to have this polypeptide that is attached to your resin, okay? And then the last thing we need to do is remove the peptide from the solid support. And the way we do that is we take a solution of 95% trifluoroacetic acid, and that will essentially remove it from the resin, okay? And we, you know, that mechanism will be discussed in course pack. All right, so let's go through an actual real-life example, and here's the task at hand. It's called thyrotropin. It's actually like a peptide hormone, and the thing, or the question is, synthesize the tripeptide using solid-phase resin with a rink amide linker. Okay. So before we start this, let's take a look at this peptide, and let's first ask the first question. Number 1, first question you should ask is, what are the key bonds that I need to make? What are the key protein / amide bonds? Okay, that we need to make. So let's look at that. So you kind of look through here. This is an amide bond here. Okay. That needs to be made through some type of interaction, and here is another one. Okay, so you can see here that's kind of divided up into 2 parts, and on this end here, this is actually the terminal, this is the terminal amide, which is the portion where this actually belonged to the ring amide portion, okay? So where are the key protein amide bonds, okay? So we've done that, 1 and 2. And then number 2 is, you know, what order and direction do we synthesize this peptide? Okay, so your trick, or your the way we do this is that this is the amide released from the ring amide, and this is our clue that this is our starting material, our first amino acid, and we have to start growing it in this direction. Okay, so because this, you can imagine this NH2 group was actually attached to the ring amide, which is attached to the beads. So what I now also suggest that you do is draw out your starting materials. Okay, so, and that's easier to see once we've identified the key protein amide bonds. So you can see that our first starting material will be this guy right here, right? So this is actually called proline. Okay, the next one, so that's 1. The next one, number 2, will be this one. So this one looks like, you know, so that used to be an amine, carboxylic acid, and this is actually called histidine. Okay, so that's number 2. And then number 3 is this last guy, which is actually an unnatural amino acid. So this one looks like here used to have a carboxylic acid. Like that, okay? So now that we've identified our starting materials and the direction it goes in, that makes life a lot easier in terms of how to generate the synthesis. Okay, so let's take a look here and start drawing how this works. Okay, so initially, here is our polystyrene attached to the bead, right? And we need to attach the ring amide. So we've done that previously, so nothing new here. Again, just redrawing it and showing you all the steps so that it's clear, right? So that goes via SN2 chemistry, and then now you are left with okay. The next thing is now removal of this FMOC group, and you can do that using 20% piperidine. Okay, so that's actually highlighted on the next slide right here. So the 20% piperidine generates the structure here. And yeah, so there should be actually an extra carbon here. And it's a good idea, you know, to draw these structures, right? It is a chemistry class, and we are learning how these bonds are made at the atomic and molecular level. All right, so now that we have our primary amine, now we can start building our peptide, right? So if we look at our first starting material, you can see that it's proline, and I'm showing it to you right here. Now, if we add proline to this mix with a coupling agent, what problem are we going to have if we simply take proline and couple this? The issue you're going to have is that this amine here can actually, with another molecule of proline, react, and then what you end up getting are potentially these proline polymers, which is undesired. So in other words, this amine here is an undesired nucleophile, so you got to protect that. So this is now, so we're going to use FMOC, and we're going to have an FMOC protected proline, and now we can do the coupling. All right, so when we do that, this will look like this. NFMOC. Okay, and then the rest of the resin. Okay, so we've put on our first amino acid. Secondly, now we need to deprotect the FMOC. So step 1, 20% piperidine. And then number 2, you go to your sort of your starting material library, and now we're going to add this histidine here. And just like we did with the first one, we have to protect this amine, right? And we're going to use FMOC again. And the other thing we actually also have to do is that if you look at our structure here, this has to be protected, protect that with FMOC, but we also need to protect this amine right here, because this is also an undesired nucleophile. So what we're going to do is we're not going to put FMOC on here, because during the next deprotection step, we don't want that to come off. So we're going to use a complementary protecting group that will be stable under basic conditions. Okay, and a good one that we learned in class is the Bach protecting group. All right, so we're using now the Bach protecting group on that side chain. All right, so once that comes together and couples with HBTU, we are now going to have our structure. So it's getting gradually bigger and bigger. That's okay though. Here's our histidine with the N-Bach. The amine and the N and the FMOC. Okay, so you can see that we're constructing our peptide. Okay, so lastly, now we need to remove this FMOC. Again, we'll use 20% piperidine. The Bach group doesn't come off. That's great. We don't want that to happen. And then number 2, we need to add that last amino acid here, this unnatural group here, to put the third portion. So we don't need to actually, because there is no actual amine on the end, we don't need to protect it. That's an amide there. So we can just use the molecule as is with coupling agent. So we treat that with HBTU. Okay, so we do that coupling off of the FMOC. And then what we need to do lastly is remove it from the resin, right? So to remove it from the resin and to cleave this bond, remember we need to use 95% TFA, right? And what else does the 95% TFA also do? It will also take care of that Bach group, right? So that also needs to get removed during the deprotection. So it's kind of a clever way to deprotect because it takes care of 2 things: removes it from the resin, and it also removes the protecting group. And from course spec, you remember that when you need 95% TFA, 2.5% water, and 2.5% triisopropylsilane as scavengers to quench that carbocation. and that will give you your product, which is thyrotropin. Okay, so I won't draw that because that's on the previous slide. Okay, but just to recall, this removes peptide from ring amide resin. And number 2 removes acid labile Bach protecting group. Okay, so that's the synthesis of this tripeptide. We will be looking at longer peptides, and you can see that there's definitely a pattern involved. Yeah, so just some conclusions and summary regarding the second unit of the peptide. So number 1, first thing we looked at was the energetics of the peptide bond synthesis. So if there's one thing I would write, it would be that, you know, amides, amide bonds, and carboxylic acids are stable thermodynamically, so need a coupling agent to raise the activation, or to raise the energy of the compound in order to lower the activation energy. Then we use that information and talked about the biological synthesis of peptides. So we learned that biology uses phosphate esters as its activated form to help facilitate this reaction. Then we talked about chemical synthesis of peptides. Chemical synthesis of peptides is more complex because we talked about protecting groups, in chemical synthesis. We talked about coupling agents and the mechanism of how that increases that activation energy. And then finally, we looked at solid-phase peptide synthesis and how you need high yields of each coupling step in order to generate long peptides. Okay, so that concludes part 2 of peptides. Next in order will be the last unit, part 3.